Hi everyone, thanks for looking at this video. Today I would like to introduce my poster for Energi Simulation 2023. My name is Fanxiang Xu from TUDelft University of Technology. My supervisors are Dr. Haji Begi and Professor Lambertus J. Slaus. The title of this poster is Multiscale Extended Finite Element Method for the Simulation of Cracks Propagation in Fractured Geological Formations. This is part of my PhD project. I would like to start this introduction with background information and then introduce the purpose we want to achieve during this research, and then what is the methodology we use, and finish with one test case presentation. So the motivation or the background of this research is to study the highly fractured subsurface formations, like one of the examples is shown in the figure 1 here. As we all know that the valuable resources such as in-house geothermal reservoir, they are often located inside the highly fractured formations. When we inject fluid or produce fluid out of these fractured formations, we may change the in-situ stress state and cause the sliding or propagation of these fractures. The sliding and the propagation of those main faults inside these formations would result in the catastrophic outcomes such as surface subsidence. So it is important for us to understand and predict the propagation of multiple fractures within the fracture formations. But consider the size of the subsurface formation we are simulating. It is often in a length scale of 100 meters or even like kilometers. And also the fractures inside those formations are often in different length scales, like those macro cracks of centimeters to the macro cracks or faults, like in the length scale of meters. So this requires us to not this requires our simulation strategy to be not just accurate but also efficient to be used to simulate the complicated fracture networks. There are still some challenges involved in simulating the fracture networks. Normally, for these complicated fracture networks, we prefer to use extended finite element method, or XFEM. Since it is a very efficient strategy, it allows us to use simple structure grids, like shown in the figure 2 here, to simulate the very complicated fracture networks. But there are still some challenges involved if we want to apply XFEM directly to geoscience applications. Because in XFEM, the extra degrees of freedom are involved in the final solution system, like still shown in the figure 2. These mesh nodes that with the markers on top of them are called the enriched nodes, and they are affected by the fractures. So to capture the discontinuities due to these fractures, we give extra degrees of freedom to these enriched nodes. When the number of the fractures becomes huge, like this is often the case in the subsurface fracture formations, we have very massive fracture networks. The number of the extra degrees of freedom is also huge. That means the computational cost for using XFEM directly to simulate the subsurface formations is very high and unacceptable for geoscience application. Therefore, we developed a novel multiscale extended finite element method, or MS XFEM method, to simulate the fracture reservoirs and fracture propagation. We want to make our method to be more efficient compared to fine-scale XFEM, but also accurate as fine-scale XFEM method. So now let me introduce the MS XFEM method. First, I want to mention what is the multi-scale strategy I'm talking about here. Instead of we solve problem directly on the fine-scale mesh, like shown in the figure 3 here, the black color fine-scale mesh, we want to solve the problem on a coarser scale, but less grid number, a mesh. That is what we call coarse scale mesh. like the red color 2x2 mesh in figure 3 here. Once we obtain the results on top of this core scale mesh, we interpolate or prolongate the core scale mesh results back to the original fine scale mesh. This interpolation process requires a key term called basis function matrix. In MS-XFEM method, we compute this basis function matrix based on the local 2D XFEM problem in each course element. This means when we construct the basis functions, we involve the discontinuities or the fractures information into the basis functions matrix. And this process of construction can be done algebraically instead of solving the local problem in each of the course 2D elements. There are two good reasons why we do this way to construct basis functions. First of all, as I have said, when we interpolate the results from core scale back to the fine scale, since all the discontinuities have been involved in the basis functions, the final solution, the final interpolated solution contains these discontinuities, since we don't want to lose details or accuracy in the final solution. And second reason is that since all the extra degrees of freedom or discontinuities have been stored in the basis functions, when we construct the core scale system, we do not need any extra degrees of freedom or discontinuities information. That means the core scale system we construct and compute on the core scale mesh is a core scale finite element system instead of core scale extended finite element system. In this way, we reduce the size of the system we use to compute more significantly. And finally, as I said, the step is to compute the solutions on the core scale mesh and prolong its results of the core scale solution to the fine scale mesh. When we simulate the fractures propagation, we only need to update these basis functions locally and algebraically on where the fractures geometries change. This whole process can be summarized into one mathematical equation. In here, the P is the basis function matrix as I have described. Sorry. To construct the core scale system or core scale stiffness matrix KC here, we use the transpose of P matrix times the original fine scale stiffness matrix KF times the P matrix. Then we can obtain the core scale stiffness matrix. Also, we use transpose of basis function matrix times the fine scale right hand side. We will have a term in this bracket that is called as core scale right hand side. The inverse of the core scale stiffness matrix times the core scale right hand side, that is a core scale solution or displacement solution in here that I just talked about. And the final step, as I've said, use the basis function times the core scale solution we just obtained. We will have an interpolated fine scale solution. Finally, I will show you one test case to check how MS-XFEM can perform when simulate the fractures propagation under compression. This is a granite sample test that contains a single fracture with different degrees inclination degree, under the uniaxial compression test. This test is based on this paper, following all the parameters and the setup. If you're interested, you can have a look. Number 4 here. The size of the granite sample is shown in the figure 5 here, and at the top there is a displacement rate control compression loading. The fine scale mesh put into this test case is 30 by 60. And for MS-XFEM, we want to simulate this problem with only 3 by 6 elements. 3 subtests are also included in here by changing the inclination angles from 30 degrees to 45 degrees to 60 degrees that are given here. First of all, we simulate the crack path using wind cracks propagation path. using only fine-scale XFEM strategy. And we want to see how this result can match with the experimental work from the paper I just showed you guys. And you can see the main wind crack path simulated using fine-scale XFEM are matching well with the experimental work. Now, if our MS XFEM can simulate the crack path identical to fine-scale XFEM, that means MS XFEM can simulate the crack propagation on the compression very accurately. And this is indeed the case, shown in Figure 7, that the red crack patterns that are the crack path simulated from MS XFEM method are almost identical to the crack patterns simulated, the blue crack patterns that simulated from fine-scale XFEM results. So we can conclude that the MS XFEM can simulate the crack propagation accurately and efficiently. Thank you for listening to this video.